Hello everyone and welcome to another episode of Investigation. In today's episode of Investigation, I will go over the quotient rule from the derivatives. I have another little practice for you guys over here, and you can pause the video if you want to try and continue watching the video when you're done. So in this video, it has f of x is equal to this, and we want to find the derivative of this function with respect of x. This is the argument of this function, which means anything except that will be left alone, meaning that if it is still a variable, let's say it is still, let's say k, but it's not the variable of the function. So then if that happens, that is just a constant. So don't let it to confuse you. If we have a y over here, then we can just use the constant rule. Constant multiple rule, actually. So f prime of x is just equal to the derivative of x cubed y plus the derivative of this thing. And obviously you can just bash it out to factor it out, to multiply it out, and do the power rule over here. But since we learned the product rule, I'm going to apply that. And I will also do the multiplying out way later. So let's do this first. So this, as I've said, this y is just constant coefficient, so that's just 3x squared y plus this thing. So we can make a little chart over here. If we have this as one of the function, let's name this as g of x. So let's name this as g of x and name this as h of x. And if we have g of x is equal to x to the fifth plus 1, and g prime of x is equal to, this plus 1 just does not exist in derivative. So that would turn into 5x fourth, and this h of x, so h of x is equal to this x fourth plus 1, and similarly h prime of x is equal to 4x cubed. And if we kind of cross multiply, you probably kind of recognize this from factoring quadratic functions. And this is a similar thing that we're going to do over here. And that would just be 5x fourth. So 5x fourth times the x fourth plus 1 plus this other. So that's x to the fifth plus 1 times 4x cubed. And if we expand that out, we get 5x. So that is multiplying, and x fourth, and that is just equal to x to the eighth plus 5x fourth plus 4x to the, that's 5 and 3, since they're kind of like that. Since they're doing multiplying, then we just simply have this as 5 and 3, which is x to the 8, I believe, and this is 4x cubed. And then if we simplify that even more, we just get 4x8 plus 5x to the fourth. So that is actually 9x to the eighth. So 9x to the eighth, 5x to the fourth, and we just have 4x cubed plus 3x squared y. And let's do the other simpler way to do this using the multiplying out method, or kind of like a bit non-calculus method. So then we have another method. F prime of x is simply equal to this. So we still have this 3x squared y, still have this. And if we have that part, we can calculate out to be the derivative with respect of x to the 9th plus x to the 5th plus x to the 4th plus 1. And that is equal to 3x squared y plus the derivative. We can use the power rule, so that's 8x 8th plus 5x 4th plus 4x cubed, and plus 1 is just gone. And if we compare our results, they're exactly the same. And that is our little practice problem for today. And let's get into our quotient rule. So the quotient rule is actually a bit hard to prove. Let's go into a new page. The quotient rule wants to find the derivative as of a function over another function. Obviously, this function does not have 0 in its range. Or if it does, then we need to exclude that in this rule if we want to use it. So let's take another intuitive sense of it, because this is the last rule that are directly proven using the definition of derivatives, and it is also the last rule, if you think about it, that is the easiest to visualize. So take this opportunity to draw yourself a good diagram. Let's try something different. Let's start with a cubic function. And obviously I'm just going to use parent function over here because that is easier to deal with. As I said, I will prove the general function, general case later for not only polynomials, every single function, as long as this thing is defined. If we have that is f of x is x cubed, and if we have another, let's say a linear function, easier to deal with. I like linear functions. So like this, then we have g of x is equal to x. If we take the quotient of them, then we would have the f of x over g of x is equal to x squared, and this derivative, we can use the power rule, and the derivative is just 2x, and this g of x, the derivative of that will just be 1, and the derivative of this f of x would be 3 times x squared. And here's what we have. We want to use this to get this. It might not be obvious straight up, but we can do some test and error, and it's not as obvious as the previous rules, but here is what we have. We actually have a very strange kind of looking formula, but if you get used to it, it's not that complicated. It's similar to the product rule. If you think about it, the quotient rule obviously does have some denominator, and the product rule is similar to the quotient rule. So it is still f of prime of x times g of x, something g prime of x f of x. So this is our product rule, but we actually don't want that in our quotient rule. The denominator function is actually going to have a derivative of negative. So like this. So if we have this, then let's calculate our function above. So f prime of x times g of x is simply equal to 3x squared minus g prime of x f of x. So that is x cubed. That is actually wrong. So it's not 3x squared. It is actually this times this. So that is actually 3x cubed. So obviously we can see we can factor out x cubed now, and obviously there's some sort of denominator. And this is just equal to, currently, just equal to 2x cubed. If we look at this, then that would be 2x cubed. So 2x cubed over x squared is equal to 2x. And x squared, obviously, we can square that. And it generally in a function does not have like a constant term, like 1/3. Obviously, there are exceptions, but it is actually the denominator function, not derivative, squared. And if you prefer a parenthesis around it to avoid confusion, then sure. So now let's prove our hypothesis. Our hypothesis is that this is equal to, so this is equal to f prime of x g of x minus g prime of x f of x over g of x squared. And if we have that, then we have to prove it, right? So if we want to take the derivative of this, so the derivative of f of x over g of x, that is equal to the limit as h approaches 0 of this h as denominator and this f of x plus h over g of x plus h. Well, this is what we're trying to prove, and that is actually just our function over here. So that is still our definition of derivative. So that's just that. And obviously you can bash it out if you want, but there is a clever trick. Let's just do the basic steps to get rid of the fraction, this kind of complicated fraction. So that's g of x times g of x plus h times h. And the numerator is f of x plus h g of x minus f of x g of x plus h. That is the result after we get the common denominator. If we continue to simplify this, then we can break it up a little bit. We can have the denominator and the numerator with the h. So the denominator part will just be the limit as h approaches 0 of 1 over gx and gx plus h times the limit as h approaches 0 of f of x plus h g of x. And if I erase some of the x's, that would be f of x g of x plus h over h. And if we have that, then let's take a look at this. We want the h to approach 0, and we've said that the value of g of x is not 0. So as h approaches 0, then this part just is gone because x plus 0 is just 0, so this part is 1 over gx squared. And the other part is still this, but we need to break it up a little bit. So if we have this, then we can simplify that to the limit as h approaches 0 of this. We need to subtract a common term and add a common term back to create the magic, what we call the definition of derivatives. So what we want actually over here is to find a common term that can form. Over here, what we have is two different derivatives. And that common term, give you a second to think about it, that common term is actually f of x, g of x. If you examine that, this part can be the definition of the derivative. And if we have that over h, then we can have the other part, which is subtract this, so f of x, g of x plus h plus f x gx. And obviously our initial terms just this times the limit as h approaches 0 of, we can factor out. So that would just simply be, let's put it in front of the limit because it does not contain h. So g of x times f times the limit as h approaches 0 of the, where did that go? The limit as h approaches 0 of x plus h minus f of x over h. That minus what we have over here is, that is actually times, so don't forget the extra parentheses over here. That is minus this f of x times the limit of h approaches 0. Because we have the minus here, this will just turn into plus and minus, exactly what we want. So g of x plus h minus g of x over h. Obviously, you're familiar with this at this point. These are just simply the definition of derivative, and that would be turned into 1 over gx squared times g of x f prime of x minus f of x g prime of x. And if you want to write it more nicely, then it just looks like this. Which is exactly our hypothesis. Thank you for watching this episode of Investigation, and I will see you in the next one. Goodbye.